So hello, and you're welcome back to episode 6 already. Wow, amazing. It's uh, it's something else when a few people start subscribing. You know the initiative you get to do more videos. But this is a part I had in stock, and I have done an article on it. So I said I'd do a video on it. So it's off a Red Bull. What was it again? An RB4, which would be 2008, I think. Yeah, 2008. Red Bull car, which would have had the R27 engine, the V8 2.4. Now, initially, as always, I bought this part. Now, as you know from following the rest of the videos, I'm solely an engine guy. So I didn't recognize this part at all when I saw it. So I reached out to, as you all know him, Craig Scarborough, world famous Formula One journalist or blogger, and he reckoned initially I thought it was from a gearbox control system part, but he thought it was steering related, and in the end it turned out he was correct. So thanks for that, Craig. So that set me down a path of finding out exactly where it was on the steering rack, because I mean it doesn't look like a steering rack to what I would be used to. So a lot of searching and contacting different people, I found out exactly where it was on the car, what it does after tearing it down, and its features and all that sort of thing. Um, Now the RB4 car is worth a mention in ways because it's got a lot of new technologies. The main one being its hydraulic system and its suspension system, which I'll might as well talk about now. Now, just to warn you, this video is going to be a mismatch of general talk about the part. Like they always say, if you're presenting something or writing to someone or doing articles or videos, to know your audience. But the truth is, I have no idea who my audience is, so I'll probably start from the start in terms of how a steering rack works, like in your own car. So if you want to skip past the first part of this video on basic steering rack theory or power steering racks, in a like a normal whatever your sedan or your normal car, skip ahead until you see this part again, because I will be bringing in the laptop into this video just to explain the basics of power steering. So if that bores you, skip on, or if you think you know it all, skip on as well. But I think you might learn something. So just to touch back again on the RB4 car, it was a 2008 car. I'll just leave this aside for 1 second. So the big thing for me with the RB4 car was it featured Multimatic dampers, which, like, this is about steering racks, I know that, but the Multimatic dampers were important at the time because unlike a normal suspension damper, they, like, as you all know, a normal suspension damper works like this. And this isn't going to take long, and I know it's about steering, but I just have to explain it because it's pretty cool. So a normal damper would be like so. So that would be your piston here. It would have oil waste through it. Just close that off. And you would have a shim stack here of various shims, and here to control the bump and the rebound. And there'd be holes through here. So there'd be a flat shim there, flat shim here. And when this would displace down, this shim would have to bend up to allow the oil through for bump. And then the rebound would be this one here, and it's controlled with a shim stack and conical spring washers, which would be these guys here. So it would be totally tunable. So your first washer would be like so. You can see there, hopefully you can see they're conical in shape. They're a spring washer, so that would hold the shim flat against these ports, which would allow oil to flow or not to flow, or to resist the oil flow. And you could stack these in a number of ways. You could stack them in parallel, like so, or you could stack two in parallel and one in series to get different flow rates. You know what the pressure required to bend this this first shim off the ports. So that's normally how it's done. Now to tune that, you have to take the whole damper apart, remove these shims, tune them, try them out, bump, rebound. There'd be different shim stacks for each one, and spring washers. So that's kind of awkward, but with the Multimatic, which I'll bring in the laptop now, it's just easier. Hopefully you can see it and there isn't too much flicker. I was going to take off this in a different video and knit them all together, but it's a huge amount of work, so let me grab the laptop and I'll explain how the Multimatic works before we get onto the power steering. So the Multimatic works with, it's a completely separate unit off the damper, and it's actually an axial spool valve is how the flow control is done. So you can see the animation there off the Multimatic website. I'm sure they don't mind. If they do, email me and I'll talk to them. But the displacement, as you can see, the fluid on the bump and rebound coming in here, the displacement is controlled through a linear motion here with two pistons. They'd be very accurately ground. And if you see this piston here on the left, that's just passing a window here. You can see it in a moment again. It just passes this window to let the fluid out in blue. So that's the window there. Now this window is important because the flow rates can be easily tuned with the shape of this window in blue that the fluid exits. So you can start off with a curve that's fairly linear and then ramp up by making the port bigger. So that's fairly cool technology compared to the normal shim stack and spring washer stack inside the damper itself. So these can be taken out easily. You can just unscrew this here, pull it out, and replace this spool valve external part with a different one with different window profiles. Now these are generally machined and ground accurately, and these windows then would be wire cut with an EDM machine, so that it's hyper accurate, so I'll just put that away for a moment again and just draw the cross section. Now again, this isn't anything to do with power steering or F1 steering racks, but it's the first car I think that featured the Multimatic technology, which is pretty cool. So in cross section, the spool would be like this, and the window then could be this shape, like so, and the piston then will be here, or the secondary spool valve. So that as that displaces linearly, you can see that at the first point, there'd be a small amount of flow, but as it takes a huge bump, the flow window would open up a large amount. And again, easy tunable. Just pull them out with the pin spanner, put in different ones, and that's it. So that's that tangent over with. So what I'll do now is do a brief explanation of power steering, how it works. I know a lot of you know this, and I probably swear now at the screen, but it's important. So I've got a range of pictures here that I took for the article. As I said, I've done an article on this part, but it's nice to do a video now just to put a voice to it, have more chats about it, and I'll be bringing in some CAD as well, just to show the simulations of how the part works and what it's like inside in CAD and both in reality. So yeah, let's go from there. It'll be a bit of a ramble, but it'll be fine. As I said, if you know how basic power steering works, just skip on until you see the part again. So what we have here is standard power, or not power steering, just a manual rack. You turn your steering, turns the rack and pinion, your hub carriers move, and your steering moves. You have a bit of a Ackerman angle there, as you can see as well, but nothing special about that. So if we move on to power steering, so a normal power steering, you're passing your car, whatever, 10 years ago now, it's gone electric now, but the principle is the same. So you would have those are the wheels. You have your steering rack here, your pressure side either side of the piston, and your rotary spool valve here, or your control valve. So as you turn the steering, you turn the control valve, which opens different windows gradually, and it pumps oil, either side if you want to turn left or right. So that pressurizes, and you've got hydraulic assistance. And again, your power steering pump here driven up the engine, and that makes your steering light. So that's very basic. Now internally, the spool valve comprises of a few parts. Now there's one important thing to note here. You would see a lot of people, I know from years ago, on the Volkswagen guys and the Audi guys and some of the Mercedes guys, they replaced their manual racks with power steering racks, but just capped them off, just to have a better ratio. Normally a manual rack would have a high ratio because it's just so hard to turn. Like it could be, I don't know, 6 to 1. So 6 turns of your steering wheel would move the rack pinion 1 turn, or move the pinion one inch, or whatever the ratio would be. But generally on a power steering rack, the ratio is a lot less. So your lock to lock turns would be a lot less for your lock to lock wheel turns. So what a lot of guys did was they replaced the manual rack with a power steering rack because the pinion ratio was less. This is a huge, they just blank off the hydraulics, use no hydraulics, and just use it for the mechanical advantage or disadvantage, just a quicker turn ratio. But as you can see here, I'll just run through the parts quickly. This will be your input shaft from the steering column. So your steering will be onto here, and this will be your output onto the rack. So this part here locates in here via a dog. So that dog is just a safety factor. If your hydraulics fail, you've still got a dog engagement into the output pinion. Now there could be, a huge amount of slack in this dog fit here between this and this, like 5 or 10 degrees, solely because it's needed for actuation of the spool valve here and the torsion bar, which we'll get to in a moment. But if you take away all the hydraulic control off it, it was ridiculous. This input shaft here would be turning this output shaft here with a very loosely fit dog. Fine, you'd have a lot quicker turn rack to rack or lock to lock, but you'd have serious play here with this dog, which is a last resort factor of safety part in terms of engagement here with the output pinion. So I don't know why guys used to do that. It was completely ridiculous, and the car in a straight ahead situation would be impossible to control, but they were happy once they had a quicker lock to lock turn, I guess. So the rotary spool valve is the common power steering control system here in a road car. So there is a torsion bar here, as you'll notice. Now this torsion bar is located solidly with the pin. It's generally here, just a cross pin. It's fixed into this lower output shaft, and again it's fixed into you can see the pin there, into the input shaft, and on that then is a spool valve. So what happens is when you turn the steering, you're actually winding up this torsion bar and turning this spool in the same time. So you've got, you can vary the feel, if you like, of the steering. So if you turn this will wind up a tiny bit. It's neck down, and it is a torsion bar, so that gives you control. So if you look closely at that, there's windows for the oil to come out, which line up with slots on the inside of this. So when you turn the steering wheel, depending on how rigid this torsion bar is, it'll turn the spool slightly, allow the oil to travel, and then turn your rack. It'll enter it into the rack either side, like the double action ram, and turn that. So that's basically how it works. Now it's one part, unbelievably, which I've made a lot of here, or done a lot of R&D on them, on how a car feels or handles going into a corner. Generally, the thinner this torsion bar is, the less resistance you'll have when you initially turn the steering, which this spool valve will turn easier, and the car will have lighter steering. Now, I think I've made about, I'd say, 100 different versions of these bars for different cars, from Ferraris to BMWs, Lamborghinis, pretty much anything like that. Um, so you can tune your steering with the diameter of this bar here. So the thicker the bar is, generally, the heavier the steering is. And it's not really a part that's ever talked about, on forums or on handling, or you know, handling systems or suspension, or the agility of the car to go around the corner. It's something I've never seen talked about, but it is completely modifiable. You can take apart all this, drive out the pin, drive out that pin, and the bar will come out, and you can basically do what you like with it. Now, obviously, it's not a safety part, because this here is still in a dog here into this. So even if that bar does break, you've got a mechanical connection here, after 5 or 10 degrees. Um, but it's something that's never ever ever talked about. They talk about dampers, springs, anti-roll bars, active anti-roll bars, weight distribution, tire widths, um, tire offsets, kingpin angle, caster angle, everything. And this one thing, I remember driving a Ferrari one time. I think it was from the factory in Maranello. It was a California, and I just remember thinking, this is terrible in terms of steering. It was just so, it was like the car was on casters on the front, really light steering, awful thing, like it was almost electric, and I just hated it. But this is a lot of the feel of your car when you're driving it or steering it. That one simple bar, it's only 6 inches long. I think the this one is from memory, I think an M3 or an M5, possibly an M3, but a lot of scope there to play around with. Their ground, it's a hardened shaft, case hardened, and then their cylindrical ground to whatever feel you want. But yeah, that's in a nutshell how your normal steering works. So let's skip on just to see in a plan view how the valving works. So you can see the internal part here, which would be, just let's get back there for a moment. So the internal part will be this part here, and the external will be the spool. So let's just go back again. So that's the internal. You can see when they turn to line up through the spool valve, the oil can exit, and you turn left, it exits into the other port, which will be these ports here, into these ones. So that's basically how that works. And again, that's left turn, you're winding up the torsion bar a good bit, and the oil can travel out, and you turn left. So that's pretty much how the standard steering hydraulic system works in a car. So now let's move on to how the Formula 1 guys did it. So we'll put the laptop away again, thankfully, said all the viewers. So as mentioned, I picked up this part without knowing what it was or how it worked. So as it turns out, this is actually a spool valve to control exactly what I described there, but it's an axial spool valve. So how does that work? What has gone on? Well, I'll show you. So in terms of size, it's 140, 120, I don't know, 100 mil, and it's got a load of connections, as you see, sensors and ports. It's billet machined from 7 or 2 series as normal. Just give you a look at there. Again, like all Formula 1 parts, if they're light grey, they're normally aluminium. If they're shiny like this part here, they're normally titanium. So it's got a lot of both in this, as you can see. There's more ports here with O-rings. There's shut-offs. There's drilling ways that are blocked off here, and there's transducer sensors here, which we'll talk about in a moment. So these would be pressure sensors. So just to put that aside again for 1 second, we should have a look at the journey of figuring out how it worked. So once I knew what it was, I set out on finding out where it was or how it worked. So if you Google, you know, F1 power steering, you get these sort of pictures. Not very helpful, and we just skim out on the one there. So you can't really see anything, because again, getting back to what I said, they don't really like showing off parts, obviously, and they're fairly safeguarded in terms of IP and design and all that sort of thing. So we just keep on. You can see it there, hidden away. Again, not sure what it does or how it works. So let's go another one. So this would be the actual rack housing itself, which would be machined from billet, and the valve system would sit onto it. It would be bolted onto it. But we'll get back to that in 1 second. So there's the rack housing again, where the tube was set, and the valve and all that. So this picture here was a breakthrough. I can't remember where I found it, but I know it was well buried in the internet, as things are when you want to look at them or when you want to find them. So I could tell this was the spool valve here, and this was the rack, obviously, and these were the rack pistons, like in the previous, you know, like in your own car. You see the pinion running through here, which the driver would sit up here. As said, the control valve here, there's a weird part here that I wasn't sure what was for. You could see the bearing here, and I was thinking, right, how could that possibly work, or what is going on? So let's keep going. So here's another picture I found, and which probably threw me the most for about, I'd say, a month, in terms of figuring out what was going on. So if you look at the input pinion here, you think, right, that goes in there into the housing, and there's a flexure here and the valve assembly here. So you're kind of going, right, you know, how can that provide any motion or movement or what? So let's move on. Here's another one similar to the last one. Again, the bearing race here, and the rack, the seals, the oil will go here and here, and the spool valve, which is inside this. And I was kind of pulling out my hair at this point, and I said, right, this has got to be a flexure, which is this part here. So I drew it up in CAD, which I'll show you in a moment. I just want to check time. How are we going? Yeah. So I drew it up in CAD and thought about it a lot, and I discovered, or got a brainwave, that right, the pinion is actually sitting in this flexure here and not in the rack housing itself. So that was a major breakthrough. So again, a close shot of it here. You would think that bearing is in the rack housing itself, but it's not. It's in the flexure, which can move, which we'll cover in a moment. Just to go on, this is the first CAD rendering I did of it, just to see was I on the right track or not, and it proves that I was. So let's go another one. That's the solid model of all the parts shown, not on wireframe. And this would be a flexure here, and the part would mount here. Now I'm going to pause the video in a moment just to break it up into halves, but this would sit here, and this flexure would control the spool valve, which I should cover shortly. So going on from that, this is it broken down. This would be your pinion here. This will be the steering rack itself and the seal areas, and the rack would surround that. And a cross section here will show the pinion, the rack. This will all help. I'll show you the CAD in a moment, but this is just to help if you want to pause it yourself on the actual parts to understand it better. Again, this is a simulation I did, which I'll do live in a moment, just to what was happening, that the pinion wasn't in fact held in the housing at all, but it was held in the flexures. So when you go to turn the steering wheel, because of the resistance from the both wheels, the resistance to turn, the pinion would actually travel along the rack momentarily and move in the, let's say, the Y direction briefly, just enough to displace the spool valve, which will be this one here. So it would move that. Let's just try a better one there. So this could move side to side independent of the housing itself, which was something else when I found out that. And again, control this spool valve, which would pump the oil from here to here, which would follow up then with the power steering effect. So let's skip on to where we were. So again, they're the flexors. That's the bearing housing just in the flexure, and the rack, the seals, where to travel. So it took a while to figure out all that, to reverse engineer, to draw it in CAD. There's the flexure again. As you see, it's got designed in limit stops here. Now, off the manufacturers supplied the spool valve that is internal to this part here that I'll show you in a minute. The displacement is 0.75 millimeters both ways, so 1.5 millimeters in total linear displacement, or axial displacement, should I say. Again, this is simulation. You can see there when you do turn the steering, the pinion tries to creep along the rack because of this resistance here to turn the wheels, and it'll actually displace the spool valve linearly or axially, which provides the hydraulic flow into these pistons here. So that was pretty cool to figure out all that. Again, these values they don't mean anything. They're just it was a rough simulation just to see how I was with the CAD and what was happening, but very cool. Again, because they did it this way, it's very easy tunable. These can be taken off, tuned for heavier, lighter, without going into the steering rack itself, as you would with your own normal road car, or again with the Multimatic dampers. You don't have to tear anything apart. You can simply just remove this part here, and you've got a whole different steering feel, heavy or light. So with that in mind, I'm going to pause the video, get rid of the laptop, and we'll bring in the actual part and tear it down. And I shall talk to you in 1 second. So okay, just to take you back to the CAD for a moment. This is the CAD model that I drew of the steering rack assembly and the flexures. Now, if I just rotate this around, by the way, because it will be asked, this is drawn in Fusion 360. It was a package that I got offered a long time ago. I got invited to Autodesk in California they were launching the product, and I got a free copy at the time and was using it for a while, but and with the intent to gather users or to recommend it. Now, if you're drawn, I don't know, if you want to draw a clothes peg and 3D print it, it's great software, but after using it for a while with various startup companies and with some established engineering companies that are using it as well, I wouldn't recommend it at all. I think it's terrible software. This is a fully licensed version. It's got all the simulation packages and sheet metal, 3D printing simulations, and I just wouldn't recommend it because it crashes, it can stall, it's got bugs, on large assemblies it can just stall out, and I would say a big no. If you're starting out as an engineering company, do not use Fusion 360. Now this is costing me, I think I kept it on because a lot of my clients use it. So if I want to get a full part 3 here, with all the parts and the colours and surface finishes and all that, I have to use it. But it costs me, I think, €75 a month, and I'll be cancelling it soon because it's just terrible. So that's a big no to Fusion 360, but that's what the part is drawn in, so let's continue on. So that's the rack. As you can see here, the main rack part here, the flexure as described, and the bearing would be here. So let's just separate off the flexure for a moment. So you can see the part there. Again, that's what I drew, just as a guess. That would be where the bearing surface goes in there, the bearing would press in there, and again the displacement movement here off the Moog specifications would be 0.75 mil, so that's what distance is there. Anything else on that part? I don't think so. Again, it's cut in aluminium 7R2 series. Let's unisolate that and turn on the housing. So let's just do a simple section cut just so you can see what I mean. So as said earlier, just to recap, the pinion is housed just in the flexures here, not in the housing at all, so it can move in the X or the Y direction, whatever way the car is drawn. So if we just cancel that again and turn off that housing and bring it into simulation, you'll see the displacement. So we'll just toggle it to that view, and hopefully this should work. There you go. So as the driver turns the steering wheel, the wheels would resist motion of the rack from left to right. So the pinion, what happens then is, because this is resisting motion, the pinion tries to creep along the rack or to climb the rack from left to right, which in turn moves the flexure here, and in turn moves the spool valve axially, which we'll get onto finally in a moment. So if I just zoom in there, hopefully it won't crash or stall. No. Oh, okay. So again, you can see the motion there. You can see the stresses here. Now it's drawn, I just guessed it, it's drawn pretty okay. The normal goal for CAD is when you put it under stress or put it under fatigue or design loads, you don't see any red areas. So if everything is fairly the same color, you've done pretty okay. So at a guess, that looks to be alright. We're down about here. So again, this is all meaningless, it's all a guess, but it gives you an idea of what's going on. So again, just before I move on to the part, as the driver turns the steering wheel, the resistance of the wheels stop the main hydraulic rod moving back to side. This tries to creep along the rack or the pinion, and in turn moves the spool valve, which will then, with this direction of oil, or with this notification, let's say, that, oh yeah, I need to move, it's going to pump oil. If it's moving this way, it's going to pump oil in here and move the rack to the right. So that's basically that. So I think I can stop that and get rid of the laptop finally. Let's just go back to design and move on to the part. So I'll do that now. So here we are at last. So we've given a brief rundown on the part already. Now let's start the parts that are falling off, as you can see. So these are pressure sensors. Now I'm not sure who they're made by. I'll just zoom in, or try to zoom in. someone might be able to make sense of the part numbers. Because I can't recognise anything. But they're incredibly badly made from a robust point of view. This sensor or this assembly has got shipped to me from the UK. Now the shipper, I know him well. He's I've been dealing with him for a long time. It was wrapped well. I knocked this part very gently off the side of my desk, and this sensor has broke. So, possibly a failure mode there. The sensor will be made here like this. This part obviously is the most important. It would have the sensor, whatever you want to call it, microchip in the nose. The PCBA then will be here in the rear, and the body of the sensor then will be stuck on there like that. This, obviously the gland wouldn't be here. It'll be filled with resin inside to bond the sleeve to the sensor, and then the wire gland heat shrink we've put in there, filled with a potting epoxy, shrunk down, and that'll be all watertight. But this just broke off here. As you can see, it's a glassy type fill, and it locates on there. And like normally you'd put a step or a ledge that would hold on there. The epoxy would link into mechanically like a dovetail shape, but no such luck. But they actually both broke. That one is broken as well, so that's pretty poor, I think. The sensors, I'd imagine, would be 5 volt in with a sense wire. You can probably see the 3 wires there. So you've got red and a black and a green. Now normally in a sensor like this, from experience, you'd have 5 volts on the red. The black would obviously be the ground plane, and the green then would be the reference voltage. So in terms of pressure, max pressure might be, I don't know what, let's just say 1000 psi, and that would be registered then on the green wire would be 5 volts maximum. So any pressure below that then would be just decimals of 5 volts below that on the green. So that's those. Again, a nice loom, again tagged with all Formula 1 parts, mil-spec connectors, nothing too special there. But that's the sensors. Now let's just screw out this one before it breaks fully. Nothing out of the ordinary sensor. It looks like stainless, probably 316, and you can see the sensor ports there, which would go on to it's probably I can't remember the name of it, but it's basically 2 silicon wafers beside each other, which measure how close they are, or how, like a pressure sensor, a pressure pad sensor. But that's those. So this is the main part of the workings of it, which would be the spool valve. So this slides in and out like so. Now the flexure is connected here, as you saw earlier, onto this, and as the flexure moves, it would control the oil in to these 2 ports here. These will be the left and right of the rack piston, so if it's, let's say if it's in that way, it'll flow out here. If it's out that way, it'll flow out here. So that's kind of that. There is a little ball joint here, which I can hopefully screw out and show you. Yeah, it will open. So you can see there's a standard ball joint there, which rides against a hardened seat, which in turn rides against a seat in there. Now this mass here, there's another one here as well which I haven't opened. This mask here, to me, is it would what I'd be called or calling a tune mask damper. It's just a mask to cut out any, as you know, this is mounted on a car which has a lot of vibrations. Um, so I would imagine this whole system would go into hysteresis, which would be the high frequency vibration of this part like that, which would possibly, do that to the steering. So this just cuts down on any crosstalk between the valve, the vibrations, and the flexure itself and the steering. So this is just a mass to add some inertia to the system, which would cut down on, as I said, axial vibrations inside the spool valve. So let's pull out the spool valve. Now again, it's nothing special. It's a normal spool valve. If any of you guys have farm machinery or tractors, the Bosch, what are they called, the Bosch Rexroth, spool valves would all be the same. So let's unwind these. They're about 5mm nuts. It's a pretty rough thread, which is surprising enough, but does the job. Again, aluminium housing, billet machined. The second one off. And third one and last one. I might have to get a wrench. I won't. No, don't drop it on the floor. So the reason these are so hard to open is because they've got a crush washer, which I'll show you. It's common. So if you see that nut there, it's a steel nut, but it's got an aluminium captive crush washer underneath it, which is swaged around it. This is just for compliance with the surface. Now, this is normally done on bolted interfaces where the bolt is very short. Now, with a bolted interface, you'd normally want the bolt really long, or the stud, where you could take advantage where the bolt would stretch, or the stud would stretch, like a cylinder head bolt or stud, where to be 4 inches long or whatever long. But in terms of very short studs where they can't go into an elastic condition, you need to be sure that you've got it fairly tight, because this isn't really stretching. It's only 5mm thick there. So you're not going to get a pre-tension on the stud there. So you want to make sure your bolts are either Loctited or have a good, mating fit with the surface. But that's those three off. So let's go with these last ones. There we go. Right, so this should pull out, hopefully. Right, so that is the spool valve assembly. If I can just take it out this side. Yeah, it should come out. There we go. And this should come off that. So internally, this is the outer spool valve assembly, and again, this is the most important feature with it. I'll zoom in on that in a moment. Just put this in here. So you can see there, that's how it'll line, like so. And as this travels axially, it will open that window, let oil in, let it out here. So let's just zoom in on that. hopefully you can see it when it's inside. You might be able to, yeah, you can. So when it displaces, it lets the oil out there, or lets the oil out there. Now again, you know, it's nothing special in terms of hydraulic part. These are common in a lot of things, but these are from, as far as I remember, Moog supplied these. This is an off-the-shelf part. Obviously this would be third party or internal manufacturer, but it's obviously it's a nice part, but it's nothing awfully special. Axial spool valve, if you want to research that, there's loads of information about it on the internet. Again, the housing, you can hopefully see the drillings inside there, which lets the oil out or in the various ways. You should be able to see them in there. Now getting to the rest of the things on this, obviously these are the dry brake connections which we're used to. I just press that with the pliers. You'll see again, like your garden hose, dry brake. We just screw that out, and you can see them there. Again, they're by Strataflex, which are common with F1 things. O-ring, chamfer, threaded, nothing special. Again, same here. Just thread them in to keep them safe. What else have we got? We've got two more dry brakes here for filling system pressure, system volume, which again, they're both the same. Take those out. So you can see the manufacturer number on there, and again Strataflex. So that's those. Same again, O-ring seal, entered with a pin spanner or a C spanner, or a pliers if you don't have either. And just screw this in there. So the part contains obviously loads of drillings, you know, and block offs. So this will be drilled in here to get a passage in there, and they intersect. These plugs then are inserted here to block off the drilling. You can see it there. There's a plug. Now the way these work is, again, they're from Lee Micro Hydraulics. I'll just draw how they work here. So you would have comes supplied from Lee like so. You'd have a plug with serrations on the outside like that, and you'd have a wedge part here with a hole here for a punch. You put that into your drilling that you want blocked. You drive this in with the press, which would push in this plug into here, and it'll expand that surface here against the bore, which would lock in the plug. So that's what those are. There's loads of them on this part. You see one there, one here, one here, 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 here. There's there's another one here. So that's how they work. So the last one will be this here, which will be an aluminium part, gold anodized, again for anti-galling, as described in loads of other videos. And underneath this is a filter. So that's the plug, and the filter should come out. Let's get the Redbull pliers. So there's your filter. So oftentimes when you've got a dry brake connection, as mentioned before, these can get dirt here, even these ones here. If you just swipe that across there, you can fill that with dirt. That interface, the little witness line there, can fill with dirt. And then when you put your fitting in there, that dirt will go into the component. So even if you've got an oil filter downline, or downstream should I say, 9 times out of 10 it will catch the oil, but sometimes it won't catch it all, you know. So that's the purpose of the filter, and it's normally on the flow line, the line in. So it's again, simple enough, nothing too special. It's got an M3 thread there to just pull it out, save using the pliers. But I can't remember who this is made by. I think it is an aerospace company in the US. Am I right? Yeah. So you can probably see there, aerospace, PAL Aerospace. So that's just a filter in there in the whole system, inserted in there. Again, you can pull it out when it's needs changing. So that threads it back in there. So that, I think, should be it with this video. We're missing an O-ring here, which will go on there. There we are back again. So yeah, that's where it mounts onto the rack, the control system, the sensors. So yeah, I think we've got it all covered. As mentioned before, in the link up there beside my LinkedIn profile, there's a buy me a coffee link. You can click in there, buy me a coffee, it helps the channel. Or you can actually buy this part, which I now will reassemble again. It's for sale on there under the commissions heading, and I shall see you all again soon. Probably, 2 or 3 days I'll have another part up. I've got one lined up, but I don't want to say what it is yet, because let's make it a surprise. So hope you enjoyed this. Subscribe, or don't bother, just send this video to whoever you think might be interested, and the main thing is enjoy it, learn from it, and I shall talk to you soon.